Hello everyone, my name is Montserrat Salvador, a master student in the material science at the Instituto de Física Ingeniero Luis Rivera Terrazas of the Benemérita Universidad Autónoma de Puebla.
Thank you for your interest. Today I will present the topic Synthesis of Composite Nanofibers of Copper and Titanium Oxide by Coaxial Electrospinning, conducted under the direction of Dr. Sergio Alberto Sabinas Hernández and Dr. Justo Miguel Gracia Jiménez. Composites based on metal oxides such as copper and titanium oxides have attracted significant interest in photocatalytic applications, as they combine the individual advantages of each phase. For example, copper oxide absorbs light in the visible region, and titanium oxides exhibit high chemical stability and photocatalytic activity under UV radiation. When both are integrated into composite using coaxial electrospinning, efficient electron-hole pair separation is favored and the solar spectrum is better utilized. In this work, composite nanofibers of copper and titanium oxides were synthesized using this technique, evaluating different copper precursors. The main objectives were to optimize experimental conditions to obtain composite nanofibers of copper and titanium oxides, to characterize the fibers structurally, morphologically, and optically using scanning electron microscopy, X-ray diffraction, Raman spectroscopy, and UV-Vis diffuse reflectance. To obtain the composite nanofibers, coaxial electrospinning was used, a technique that allows two solutions to be processed simultaneously using concentric needles, one for the core and one for the shell. In this case, titanium oxides from the shell and copper oxides from the core. The coaxial electrospinning system includes high voltage source, syringes with polymer solutions, needles connecting to the voltage source, infusion pumps that control flow, and a collector connected to the source which receives the formed fibers. Coaxial electrospinning consists in applying a potential difference between the concentric needles at the collector, which stretches the polymer solutions, forming a continuous thread composed of different materials, as shown in this image. To perform coaxial electrospinning, the first step is the preparation of the polymeric solutions. For the titanium oxide solution, first 2.5 milliliters of ethanol and 1 milliliters of acetic acid are mixed. Then 0.70 grams of PVP are added and stirred. After that, 1.75 milliliters of the mixtures are taken and 0.75 milliliters of titanium butoxide are added. Finally, the solution is sonicated and loaded into the syringe. For the copper oxide solution, we replicate the base of the titanium oxide solutions, testing different copper precursors, as shown in the table. Only copper 2 acetate monohydrate exhibited good solubility. First, 2.5 milliliters of ethanol and 1 milliliters of acetic acid are mixed, and then 0.1 grams of copper 2 acetate monohydrate are added, followed by sonication to ensure complete dissolutions. Next, 0.15 grams of PVP are incorporated in the stirred until the solution is homogeneous. Finally, the solution is loaded into the syringe. Once both solutions were ready, they were placed in the separation singers connecting to the concentric needles, which in turn were attracted to the infusion pumps and the high voltage power supply. The collector was positioned below the needles and also connected to the power supply. Electrospinning was carried out by applying 50 kilovolts with a fixed outlet flow rate of 0.3 milliliters per hour and inner flow rate that varied between 0.3, 0.2, and 0.1 milliliters per hour in order to obtain 3 different compositions. Afterwards, the fibers were calcined at the 415 degrees Celsius for 3 hours to remove the PVP and obtain the crystalline phases of the oxides. For this work, 5 types of SEMs were synthesized: pure copper oxide, pure titanium oxide, and 3 coaxial nanofibers labeled M1, M2, and M3. In the latter, the external flow was kept constant at the 0. milliliters per hour, while the internal flow was varied for each case: 0.3 milliliters per hour for simple M1, 0.3 milliliters per hour for sample M2, and 0.1 milliliters per hour from sample of M3. Based on these synthesis conditions, the expected nominal composition of each oxide in the composite nanofibers was calculated, as shown in the table. We use scanning electron microscopy to analyze the morphology of the samples. Image A shows the micrograph of the copper oxide fibers, which exhibit a fibrous morphology composed of the interconnected grains. Image B displays the typical morphology observed in titanium oxide fibers as well as in the copper titanium oxide composite fibers. The average pipe diameter of each sample was determined using Image J software and compared with of titanium oxide fibers. As shown in these histograms, the average diameter of the titanium oxide fiber is 97 nanometers, while the average diameters of the coaxial samples are 82 nanometers for M1, 102 nanometers of M2, and 93 nanometers for M3. These results indicate that variation in the internal flow rate directly influences the fiber diameter. For the optical characterization, absorption was evaluated using the Kubel-Kammon fusion. The results showed that the composite sample, represented by the red, blue, and green lines, exhibit absorption in the visible region, in contrast to the pure titanium oxide samples, black line, whose absorption is mainly restricted to the ultraviolet region. Based on this behavior, Raman spectroscopy was performed. In this spectrum, the red, blue, and green lines correspond to the composite fibers, while the black line corresponds to the pure titanium oxide fibers. Vibrational modes characteristic of the ellipse and rutile phases were identified. However, in additional modes, a 278 was also observed, which doesn't belong to any titanium oxide phases. To clarify this result, structure characterization was carried out using X-ray diffraction. The obtained spectral revealed the presence of copper in the ternary phase, together with the ennetase and rutile phases of titanium oxide, as shown in the image. The next step of these works will involve a more detailed analysis of the diffraction spectrum through Rydberg refinement in the order to determine additional structural parameters, including the unit cell size. To close, I would like to highlight the main conclusions of this work. Composed nanofibers of copper oxide and titanium were obtained using our methodology. The use of copper acetate monohydrate to obtain copper oxide provided an efficient route for the synthesis of composite nanofibers of copper oxide and titanium by coaxial electrospinning. The resulting materials exhibited a continuous fiber morphology. Spectral obtained by UV visible diffuse reflectance spectroscopy showed significant absorption in the visible light range, and samples containing copper oxide exhibited a dark color. Micro-Raman analysis of samples M1, M2, and M3 confirmed the presence of the ennetase and rutile crystalline phases of titanium oxide, as well as the monoclinic phase of copper oxide. Furthermore, X-ray diffraction showed NHAs to be majority phase, with rutile and brookite phases present in minor proportions. The presence of mononucleic copper oxides was also confirmed. We thank Dr. Laura Elvira Serrano de la Rosa and the FAB Central Laboratory for support with Raman and UV Visible Diffuse Reflectance Spectroscopy and the Laboratorio de Refinamiento de Estructuras Cristalinas UNAM for X-ray diffraction measurements. Special thanks to Dr. José Guadalupe Pérez Ramírez, head of the laboratory, and Mr. Antonio Morales Espino for their technical assistance. I would like to thank CECITI for the master's scholarships. This work was funded by BF Thanks for your attention.